We have a new optimizer called as Adam Mini. Before I tell you about this optimizer, let's have a quick look at what exactly is meant by this optimizer in layman's terms. In machine learning or in these large language models training, an optimizer is a very important component that helps adjust the model's parameters to minimize the difference between predicted and actual values. This difference is also called as training loss. The optimizer iteratively updates the model's weights to find the optimal combination that reduces the loss, leading to improved model performance. For example, let's suppose you are training a model from scratch. Initially, the model's weights know nothing about the data which it has been trained on. You just randomly initialize them with some random seed value. Now, let's say you ask the model what is 1 plus 1. Initially, model wouldn't know. It is just a weight. So it will just say, let's say 3, which is a wrong answer. Now, it is a job of optimizer to iteratively make sure that model reaches to the correct answer, which is 1 plus 1 is equal to 2. And the way it bridges the gap between the predicted value and the actual value is called as learning. And this is what the job of optimizer is. AdamW is a popular optimizer in deep learning, which is an extension of the previously Adam optimizer. AdamW adapts the learning rates for each parameter individually like Adam, but also includes weight decay. Weight decay is also called as L2 regularization in more technical terms. AdamW is quite good at reducing overfitting by adding a penalty term to the loss, plus it improves generalization by shrinking model weights. AdamW is an optimizer that adapts learning rates for each parameter and it reduces overfitting by adding weight decay, and that is what AdamW does. Now, we have Adam Mini. So what is wrong with AdamW? AdamW definitely has become the de facto optimizer for training LLMs. Despite its superior performance, AdamW is an expensive optimizer to use. AdamW or Adam requires a memory for its optimizer states, the first order momentum M and the second order momentum V square. These in total take at least 2 times the memory of the model size. This memory consumption has become a major burden in LLM training. For example, to train a 7 billion model, Adam alone requires about 56 GB per card, GPU card for M and V. And with the gradients included, a total of 86 GB is needed. This is expensive even for cutting edge graphical cards like A100 or 80 GB because A100 and Nvidia's A100 GPU card has only 80 GB of VRAM. So even for training a 7 billion model with AdamW optimizer, you would need 86 GB. So it means you need multiple A100 cards, and these cards are expensive. These are not cheap. To support the high memory algorithms, CPU offload and sharding must be used in practice which unfortunately increases the latency and slows down the training. The situation further really becomes cumbersome when training large models like Palm with 540 billion parameters. It becomes way expensive. For example, for Palm model with 540 billion, Adam optimizer requires more than 50 GPUs, and each GPU would have 80 GB of VRAM. So you can imagine how expensive it would become. That is where this research proposes this Adam Mini, which is a new optimizer. Adam Mini partitions the model's parameters based on principles that, according to Hessian structure, this is a machine learning structure, and then it chooses a single learning rate for each block using the average of Adam's V in that block. Adam Mini has various advantages. For example, Adam Mini is lightweight. By design, Adam Mini largely reduces the number of learning rates used in Adam. And for mainstream LLMs, Adam Mini could cut down more than 90% proportion of Adam's fee, which saves around 40% to 50% of the memory cost of Adam. Despite the memory cut down, these researchers have empirically verified that Adam Mini performs on par or even better than AdamW on various language model sized from 125 million to 7 billion, including pre-training, supervised fine-tuning, and reinforcement learning from human feedback. Adam Mini also reaches better performance on non-LLM tasks such as training diffusion models, vision models, and graph neural networks. And these are few of the algorithms where you can see it in action in PyTorch transformers. Adam Mini can reach higher throughput than AdamW, by the way. And there are a lot of benchmarking which they have done. One principle which really intrigued me was partition principle, which is a key component in Adam Mini, and it is a strategy for parameter partition. And they have proposed to partition parameters based on the smallest dense subblock in Hessian, and this principle can apply to generic problems. For problems with block diagonal structure, they have found out that more learning rates do not necessarily bring extra gain, in particular for the problem associated with each dense subblock. A single but good learning rate is more than enough to bring better performance, which I agree with in one way or another. Now, they also have a GitHub repo where they have shown some of the examples and as how you can go about using Atom Mini Optimizer. For example, here they are importing Atom Mini from this GitHub repo and then they are specifying these parameters. For instance, model is a model which we are going to train. LR is for learning rate, and this is the rate that or step size for each iteration, and it controls how quickly the model learns. And then we have weight decay, which is a L2 regularization strength, and that adds a penalty term to the loss to prevent larger weights. And then we have defined beta 1 and beta 2, which are the hyperparameters for Adams Mini's adaptive learning rate algorithm. Beta 1, the default value is 0.9. It is an exponential decay rate for the first moment, mean of the gradient. And beta 2's default value is 0.999, and that is exponential decay rate for the second moment, or V, variance of the gradient. And then we have epsilon, which is a small value added for numerical stability, and that avoids division by 0. Then we have 0_3, which is a Boolean flag, which I'm not really sure what exactly that does, but I need to read their GitHub repo. So there you go. So it is that if you are using 0.3 in deep, okay, so this is related to deep speed parallelism, so which you can check out. Then we have nembed and nHEAD. So nembed and nHEAD, these are related to model architecture, which specify embedding dimension, attention heads, and the query groups. So by defining these parameters, what we are doing, we are customizing the Adam Mini optimizer for this model. And then they have few examples where you can start the training for GPT-2 models, Llama based model, and few other very new projects. So I'm more than sure that this is going to be evolving more, but interesting, and especially when it is saving us money and time in terms of memory. That is amazing. So that's it, guys. I hope that you enjoyed it. I'm going to put the link to this research and video description. Read through it, let me know what do you think. If you like the content, please consider subscribing to the channel, and if you're already subscribed, please share it among your network as it helps a lot. Thanks for watching.